Okay. What question was it that you were asking?
31. If you want, I can just like tell you.
Tell me what it says.
Yeah, so it's square root of 9. And then under that square root, minus square root of omega, 49.
49?
Yeah. Then minus, no,
Is this...
on that same square root, you do minus square root of little omega. There you go. Now out is minus 7.
Out here?
Yeah. Over
everything divided by
2 little omega.
What are we supposed to do here?
Approximate.
Approximate. Okay. So notice the denominator approximately equals the denominator. What about the numerator?
49, square root of 49.
Okay, so notice what happens when you do this. Something's going to happen that we don't necessarily want, right?
0.
What does this violate? Yes. It violates the approximation principle. So we don't do that step. That step is, for our purposes, not correct. So what you want to do is go like this. Okay, we have 49 minus the square root of omega, little omega, minus 7 over 2 omega. This necessitates multiplying top and bottom by the conjugate of the numerator. I mean, we've been doing this over and over again. What ends up occurring is in the denominator we get this. In the denominator, what you end up getting is when you FOIL it out. Because this times itself is the thing without the radical. Then the middle terms cancel, and then you get the last term, 49, is 7 times negative 7. Okay, so these cancel. And we get negative square root of little omega all over this 2 omega times this square root of 49 minus square root of little omega plus 7. Okay, so what now?
When you simplify those,
Say what?
I don't know. I was gonna tell you we'll simplify, but I didn't realize. I forgot that it had the square root. I don't know how to do that. Yeah. No problem.
This is what happens when you distribute the 2 omega, right?
Mm-hmm.
Now what?
Oh, did you drop it one? Oh no, don't think that.
So take a look. What is negative square root of omega the same thing as? This is the same thing as And what is 2 omega the same as? So what happens when you cancel those? Because notice that omega to the 1/2, if we got a negative on it, divided by 2 omega to the 2 over 2 is the same thing as negative omega to the 1/2 times 2. We'll keep the 2 down in the denominator actually. Times omega to the negative 2 over 2. Like bases, whenever you multiply them, their exponents add. So this becomes negative omega to the negative 1/2 all over 2. And negative omega to the negative 1/2 all over 2 is the same thing as negative 1 over 2 square root of omega. So just looking at these two terms, it turns into negative 1 over 2 square root of omega. This is all pre-calc stuff. You know, like if we have x, and this is to the first power versus x to the negative 1 power, that's the same thing as 1 over x. If we have x squared, then x to the negative 2 is the same thing as 1 over x squared. If we have the square root of x, it's the same thing as x to the 1/2. And if we have 1 over square root of x, it's the same thing as x to the negative 1/2. Also, the fact that let's say a to the power of x times b to the power of y, when you multiply a to the power of y, when you multiply like bases, their exponents add. Those are all pre-calc, pre-algebra. So when you apply this stuff, notice that these two quantities combine, and actually, I didn't need to distribute here like I did right here. We'll go back to right here. Prior to distributing this 2 omega to each term, these two combine to give us this right here. Negative omega to the 1/2 power. So what does that mean? When I have square root, negative square root of omega all over 2 omega, I'll do all the calculations again. And I'll do it in a yellow box, so you guys see it all over again, because I'm sure this step is confusing. This is the same thing as negative omega to the 1/2 power, all over 2 to the omega to the 1 power. Okay, but 1 is the same thing as 2 over 2. Okay, but if I want to bring this upstairs, I got to put a negative on it. I'll keep the 2 downstairs. Like bases, when we multiply them, the exponents add. So 1/2 plus negative 2 over 2 is the same thing as negative 1/2. If we want to get rid of that negative in the numerator, in the exponent, what we can do is say that this is negative 1 over 2 times omega to the 1/2. Again, this is the same thing as negative 1 all over 2 square root of omega. So now this board is jumbled up. That part should thoroughly make sense now. So we were at this step, right? Now that step decomposes to, those two things in yellow combined to just give me this negative put a negative here. 1 all over 2 square root of omega times what we had there, square root of 49 minus square root of omega. Close the square root plus a 7. So that's what we have. Recall that this negative is the same negative that used to be here. We got the yellow things and we combined them to get us this algebraically. So that negative still retains itself over here. But now we have a 2 square root of omega in this business. So notice what happens. Here's another property in algebra that you might have forgotten, is that the square root of AB is the same thing as square root of A, square root of B. Okay. Also, the square root of ABC is the same thing as square root of A, square root of B, square root of C. The square root just goes through multiplication just like that, and in reverse. Okay. So notice that now we can say that this is equal to 2. Rewrite this. This is negative 1 all over 2 times the square root of omega, square root of 49 minus square root of omega. Close that plus 7. Moving the calculation over here, I get negative 1, everything divided by 2 times the quantity. So this omega, if we call everything in here B, and this is just omega, it's as if you have this square root of omega times square root of B, where B is that 49 minus square root of omega. But according to algebra, that's the same thing as this. Omega times B, where B is 49 minus square root of omega. So that means we can include that term all under the same square root, where this becomes omega times B, but B is 49 minus square root of omega. Okay? But, see here. Originally we had this. So we're keeping the 2 out and we're distributing the omega to this term, but then the omega also needs to be distributed to this 7th term. Don't forget that. Okay. Don't forget that the omega, square root of omega that is, has to get distributed to this term as well. So this needs a square root of omega. Okay, so we're keeping the 2 out, distributing the square root of omega in. So that combines like so, and then the 2 stays out. The square roots go under one big square root, so you get this. And again, yeah, that's correct, because your B is your omega. Your B is this whole thing. So this is going to be square root of omega times B. Okay, so that's done right. And then we have to say this is plus a 7 omega, square root of omega. And it will close the parentheses here. What happens when you distribute this omega? Here, that's the next step. So then you get 49, so this is the square root of 49 omega minus, what's omega times square root of omega? Huh?
Omega? No.
No. No. Oh yes, it is omega squared of omega, but notice that
Omega.
this is like this times this. So the exponents add because the bases are the same. So this becomes 2 plus 1 all over 2. So it becomes omega to the what? 3 over 2. Right? Okay, so minus omega to the 3 over 2. Feel free when you're doing these problems to like do side calculations. It's very necessary to do some side calculations. Okay. So we got 49 omega minus omega to the 3 halves. When I distribute this omega, that's it buried inside the square root. But then we just repeat this plus 7 omega right here. And then close the parentheses because that 2 technically has not distributed through yet. Now that we've done that, the important part of making sure we did all this stuff is to figure out what is on what level, right? Because now we can start approximating what's inside that square root. We can start approximating those terms away. Okay, so 1 is approximately 1. What can we approximate with here inside that square root? Which one is on the higher level? 49 omega or omega to the 3 halves power? So here's the real level. Here's the omega level. Taking the square root of omega brings it closer to the reals, right? So what about omega to the 3 halves? Does that also gets closer to the reals, right?
No.
Huh?
No.
No. Why is it no?
Because it's like if you were like going, if you go up on that, it makes it smaller. So that's why it would go down. Because you see how you have 1 half on the top, and then the other one is 1, like the one on the bottom is like 1, right? So if you want to keep going like that, then you would need to, yeah, there you go. So then you would need to have 3 on the bottom.
Aha! Aha! This is our normal omega, but we're calling it omega to the 2 over 2, which is omega to the 1, which is just omega. So this is on the lower level, huh? So we can approximate it out. Very good. Remember, you see why I was taking it slow with this concept? Because you have to apply it to solve the problems. You have to apply the concept very deeply to solve the problems here. Okay? So now that that happened, I'm going to approximate again. What can we approximate again? -1 is just -1. Notice that here, let me do 2 times the quantity. Approximately. Notice that square root of 49 omega, what is this the same thing as? This is the same thing as square root of 49 square root of omega, which is the same thing as what? Excellent. Good job, guys. 7 omega. So this breaks down to just 7 omega. Plus 7 omega. Yes. Good job.
But wouldn't it be square root of omega? Because it's not like omega squared. No.
Oh, yeah. No, yeah, you're right. This is a mess up right here. This should say root omega. Yes. This should say root omega. Yes. There we go. Okay. So really, there was no approximation here. There was no approximation at this point. We were just doing equals. So we go from there, we approximate, Well, I don't know where that step was. No, there was an approximation. This was approximated, okay? So it was an approximation. All right, so now what happens? Now we will approximate again. If you'd like, we could distribute that 2 already, actually. We might as well distribute that 2 now. So this becomes a 14 omega plus 14 square root of omega. Okay. And again, actually, this time we didn't approximate. This is just the equals. Now we will approximate. -1 is approximately -1. How can we approximate that denominator? Say what? 14 square root of omega. Are you guys implying that the square root of omega is on a higher level than omega? You're right. Boom. So you're saying this is 14 square root of omega. Okay. Now what?
I think that's it. I think. I would hope. It's like a long process.
Yeah. So what was the question asking? Just approximate?
Just an approximate.
Are you trying to render a real result?
No, just
You're not trying to render a real result? Okay. If you're not trying to render a real result, we're done. It's approximately that in terms of hyperreal numbers. We're not trying to render a real result. Okay, so if all this stuff was kind of tricky, the tricky stuff gets involved when you have to activate college algebra stuff. So the concepts that we went over is like college algebra stuff. So that's you can review that stuff. There's like my YouTube channel where we talk about that on my YouTube channel. There's other YouTube channels. There's other websites. You need to review the college algebra stuff for that. Okay, so that's why they typically call that stuff pre-calculus, and this is calculus, because you have to master that stuff to be able to do this. Okay. Does that make sense? Okay. This long, yeah. Okay. Okay, well, that was a 22-minute explanation there, but it's good because
Yeah, good.
it helps you guys learn. So we were talking about limits. Limits. Where do we drop off? Oh, I marked it. So we were talking about that sine case. So what is the limit as x approaches 0? X sine of 1 over x. Where if we evaluate, this is our f of x. If we evaluate f of 0, we get 0 times sine of 1 over 0. Obviously, that's not a good thing. Okay, we talked about the transfer principle, implying that we can evaluate f of alpha, which is alpha times sine of 1 over alpha for an arbitrary infinitesimal. Okay, so then by the transfer principle, we say that, okay, the sine of 1 over x is always in between -1 and 1. This is true, right? For those of you, I mean, everybody should have taken trigonometry. You guys know this, right? Okay. Okay. So then, by the transfer principle, this implies that this is true. Which then, if I multiply both sides by alpha, all sides by alpha, multiply all sides by alpha, we get this. But this is indeed exactly identically f of alpha. So we know f of alpha is between negative alpha and positive alpha. Because alpha is arbitrary, this is in the case if alpha is greater than 0. In the case of if alpha is less than 0, then alpha is negative. And so multiplying both sides by alpha would flip some signs here. This is just so we can cover all bases here. This is just taking into account that alpha is an arbitrary infinitesimal. It can be positive, it can be negative. If we multiply by something so arbitrary, we have to denote it in 2 separate cases, because technically either of these are possible. Only when we fix what alpha is, whether it's positive or whether it's negative, do we know which one of these cases it will be. So that means our function f of alpha, whatever its value is, it's between negative alpha and positive alpha. So that means it has to be an infinitesimal, because whatever infinitesimal alpha is, only an infinitesimal number can fit between 2 infinitesimal numbers. All right, in magnitude. So what does that mean? What does that mean? What can we render the real result as?
0.
Why?
Because if you render the result of an infinitesimal number, it's always 0.
Yeah, this is some infinitesimal. We've proved it. It's wedged between 2 infinitesimals. And if I ask you render the real result of alpha, as this young man just noted, you would have to say 0, right? So if this is an infinitesimal right here, because it's in between 2 other infinitesimals, when you render the real result of it, it should equal 0. So thus we have figured out what the limit as x approaches 0 of x sine of 1 over x is. It's equal to 0. This is typically called the topologist's sine curve. Can I erase? I'm just going to erase everything except the function. So the graph of this function is like this. Very beautiful graph. That's what it looks like. Is your f of x is in yellow. So we wanted to see, what is this crazy thing doing as it gets close to 0? It's getting small. It's basically becoming nothing. Isn't this cool? Isn't math cool? Look at how beautiful and artistic this shape is. Really, it correlates to a trigonometric function. It's really cool. It's only when me personally, it's only when I realize that math correlates to cool shapes like this. This is when I start to really find math cool. Is when I realize that the stuff that we're talking about correlates to shapes and ideas and things in your imagination. This is cool. Okay. So what does that mean? So is there a hole here or is it solid? At 0. At 0, 0, at the origin. Is there a hole there or is it solid? There should be a hole. Why?
Like it's undefined, if you do like 0, like if the f of x is equal to 0, then, you know, it's like undefined. 1 over x, I mean, not 1 over 0 is undefined.
When was the case where there wasn't a hole and the limit was the value of the function?
You basically asking when it was, like, when it wasn't a hole, like when it's closed, basically. That's when f of x was equal to the output that we have.
Yes, that's right. But f of x is undefined in this case, right? At 0. If f of 0 was defined, it would just be solid. There would be no hole. But f of 0 is non-defined, not defined. So that's why there has to be a hole there. The limit exists, which tells us what is it a little to the left and a little to the right. Remember? Well, at 0, it's undefined. So there is indeed a hole there. Very good. Let's do another example. The limit as x approaches 1 of 1 over x minus 1 divided by x minus 1. Remember, this is the same thing as saying evaluate f of 1 plus alpha, which is the same thing as 1 over 1 plus alpha minus 1 divided by 1 plus alpha minus 1. These cancel, and I get 1 minus the quantity 1 plus alpha, everything over 1 plus alpha divided by alpha. So then distribute this negative here. We get 1 minus 1 minus alpha all over 1 plus alpha all over alpha. 1's canceled. So you get a minus alpha all over 1 plus alpha all over alpha. Alpha. Say what? I hear mumbling.
I had put the wrong thing. Instead of putting alpha, I had put x, so I had to go back.
Oh, okay. So now I'm just going to rewrite it. Negative alpha over 1 plus alpha, everything over alpha. So then we got to multiply by the reciprocal. So then the alphas cancel. So you just end up getting negative 1 all over 1 plus alpha. What does this render? What is alpha compared to the real number 1? It's nothing. Compared to the real number 1, it's nothing. So it just goes away. It's insignificant. So what does that answer? It renders the real result negative 1. So the limit as x approaches 1 of 1 over x minus 1 all over x minus 1 renders the real result negative 1. So let's talk about an example, the limit as x approaches 2 of x squared plus 1. Okay? Again, this is like saying, well, evaluate f of 2 plus alpha. That's the same thing as 2 plus alpha, quantity squared plus 1. That's the same thing as 4 plus 4 alpha plus alpha squared plus 1. This is the same thing as 5 plus 4 alpha plus alpha squared. Which renders the real result what?
Would you approximate that first?
Yes,
So,
you can approximate.
so 5?
Yeah. So it ends up rendering the real result 5. When we render the real result, we approximate right away. First order approximation, second order approximation. We just go to the real result. Basically, we throw away all the infinitesimal pieces. We want to see what is the real piece. And when we say that, it's kind of like, the real piece, like it's a lie. The real piece is this. This whole thing is the real piece, the true piece. But by real piece, we mean real number. That is the real result. But this is rendering the real number system result. So the word is not to be confused with the concept. The concept of something being real versus not real, true versus not false. I would say that this is a more real quantity compared to this one. But this is rendering the real result projection onto the real number system. Okay, so would this graph have holes in it or not? Because really what it makes is this parabola. Does it have a hole?
I mean, if it's rendered,
Here at 1 and 2. Is there a hole here? No. Why?
because that's a real like answer.
You can plug 2 into
Yeah.
Aha! Say that louder, young man.
You can plug 2 into the original equation.
F of 2 would equal 2 squared plus 1, which is 4, plus 1, which is 5. And that's a real value result. That's why. Because evaluating the function at 2 and taking the limit of the function at 2 agrees. They agree. If they don't agree, that means there's a hole. Especially if when you evaluate it, it's undefined. There's definitely a hole there. If you evaluate it and it's undefined, but you take the limit as x approaches that number and you get a limit value, then that means that at that value it's undefined, but around it, it's defined. So let's do an example like that. Calculate the limit here. Notice that if we just plug in f of 3, it ends up becoming this. Is that good? Not good. Not good at all. But when we calculate the limit, Threes cancel. Threes cancel. What does this equal? Sometimes. Sometimes it equals 1. Sometimes it equals -1.
Oh, you're right. Yeah. Good luck.
So let's talk about this. It equals 1 if what?
Greater than 0.
If
Let's see. If alpha is greater than 0,
yeah,
what happens?
that
It's positive, right? So absolute value of alpha over alpha just gives me alpha over alpha, which is 1. So if alpha is greater than 0. So it equals -1 when?
Less
Because then if this is true, because remember alpha is arbitrary. Makes sense? We don't know if alpha is positive or negative. So we have to entertain both cases in which it's positive or it's negative. It's not 0, so we don't have to entertain the case when it's 0. We do have to entertain the case whether it's positive or negative. What kind of graph does this make? What kind of graph does this make? Recall, we were taking the function, the limit as x approaches 3. So all this business is occurring is at 3. So what is f of 3 if alpha is positive? 1. So is it defined at 3? No. And it just stays 1 forever, doesn't it? Because x minus 3 is greater than 0 if x is greater than 3. Greater than or equal to 0 if x is greater than or equal to 3. But x can't be equal to 3, so we have to remove it. We know when it does equal 3, it's undefined. That's where the hole is. This is referencing the definition of absolute value. So for values of x greater than 3, the output of the function is a positive 1, because really this is like a ratio of itself over itself. And over here, this is positive 1. Here's -1. We're going to have a hole here, and it's just going to go this way forever. Because x minus 3 is less than 0 if x is less than 3, making it -1. So, yeah. Did you guys get my email about the test being over chapter 1? I sent out an email to you guys where the test is going to be over chapter 1. So sections, all the way up to section 1.8. That's not what it says in the syllabus. But as I said, it is very tentative. So we're in 1.4. We're nearing ending 1.4. So there's 4 more sections left. But yeah, I could definitely see a concept like this on the test. Take a limit, determine where the holes are, graph the function, something like this is very possibly on the exam. Probably shouldn't have erased that. All right, 3 and 1, -1. Because this allows us to segue to the next concept of one-sided limits. Notice that we've discovered that the limit as x approaches 3 Why did we discover that it does not exist? We discovered that it equaled 1 for values of x greater than 3 and -1 for values of x less than 3. Why is it that I'm now claiming that it does not exist? I thought we found numbers that are associated to it. 1 sometimes and -1 sometimes. Why does it not exist?
Because if you plug 3, you're not gonna.
Well, that's why there's holes here, that's for sure. But why, in terms of the limit, does the limit not exist? We're saying that the limit does not exist.
Because there's 2.
Yes, because there's 2. Because the function breaks apart into 2 pieces. This is what we call the jump discontinuity. It's discontinuous, you jump. So this gets into the fact that there's a left-handed limit and a right-handed limit. Left-handed limit is approaching the number 3 from the left, which gives you -1. A right-handed limit is approaching the number -3 from the right, which gives you +1. So the limit does not exist because the right-hand limit and left-hand limit don't agree. So the limit as x approaches 3 from the left is how we describe that as a left-handed limit. We would say that that equals and then we say that the right-handed limit, notice the superscript minus means from the left. The superscript plus means from the right. These limits are not the same. And that implies the total limit that implies the total limit DNE does not exist. Yes, does not exist. So notice there's no superscripts here, but there are superscripts here and here, indicating the left limit and the right limit.
So anytime a limit jumps from basically negative to positive or doesn't connect in a way, it does not exist.
Correct,
Okay.
because it might have a left-handed limit or a right-handed limit, but the overall 2 limits have to agree for the total limit to exist.
Mhm.
This is the total limit. So now let's talk about how do you approach it from the left and how do you approach it from the right. This is going to have to make us switch from alpha. Alpha is too arbitrary for this purpose. Alpha made us have to break it up into 2 different cases. So we're going to have to switch from alpha. Let's define what I'm talking about here. This could be a test problem. Like it could be like, oh, evaluate this limit. If it does not exist, explain why. Thoroughly explain why. This could definitely be a test problem. So let f be a function, be a real number. If f of v plus omega is defined and renders the real results B or L, renders the real result L. For every positive, omega. Remember, this means for every. Or for all. For every or for all. So if this is true, that implies that the limit as x approaches b from the right of f of x is equal to L. So what that means is that f of b plus omega ends up rendering the real result L. By the same token, the limit as x approaches b from the left of f of x, if that equals L, this would imply that f of b minus a omega renders the real result L, where omega is a positive. Omega is always positive. It's not like alpha where we don't know what it is. We know omega is a positive hyperreal number, so that when there's a minus in front of it, this is to the left of b. And when there's a plus in front of it, this is to the right of b. Hence the right-handed and left-handed limits, respectively. So if this occurs, the left-handed and the right-handed limits both agree, we say that the total limit exists and it equals L. But if the left-handed limit and the right-handed limit say two different values, then the total limit does not exist. Class is dismissed. I'm a few minutes over time. So this section is taking a little longer than I hoped. That's okay. I prefer you guys know it really well than to blow through it and adhere to some arbitrary schedule. We don't have much left in this section, actually. For which one of these is it? Which section? 1.2. Okay, that's fine. I probably will give you an extension for section 1.4. Thank you. Yep.